All right, welcome. This is the first lecture of Mechanics of Materials, otherwise known as D-Forms. This crash course will follow the Virginia Tech ESM 2204 curriculum, which is pretty much the same as any other D-Forms course you find in an engineering university. This course piggybacks off of statics, right? So in statics, of course, we utilize the no movement, right? Acceleration is equal to 0. And we only talked about forces and moments on the outside and inside of systems. So recall that we spent a lot of time looking at equilibrium problems where we found the reaction forces and reaction moments of any particular system and support. We also looked at frames, machines, and trusses, right? So we looked at several methods to understand and analyze those. In addition, we talked about some other tools such as area moment of inertia, centroids, and some internal stuff with beams like shear moment diagrams. Well, we are going to be using almost all of those tools in here in our D-Forms course, all right? So the D-Forms curriculum will cover the following. So in the first lecture, we are going to talk about an introduction to D-Forms, and most important part of this lecture is going to be what I call the flow of D-Forms, all right? The next lecture, we're going to be talking about properties of strain, okay? And then we're going to be talking about stress, and then torsion, and then bending, and then transverse shear and combined loadings, and then stress transformations, and lastly, we're going to wrap the course up with buckling, all right? So of course, you probably have no idea what any of those things mean right now, but that is the curriculum in a nutshell. So the first thing that we're going to do is I want to go over the flow of D-Forms, okay? And if you remember nothing else from this course, this first, whatever, 10 or 15 minutes of this lecture is what I want you to walk away with this entire course with, okay? Because this flow of D-Forms is not something that is taught in school. It is something that I came up with to help tie together all of the material that we covered in statics and that we are going to cover in D-Forms. In addition, this D-Forms is sort of a middle step between statics and the final course, if you will, that is mechanical design. And even if you are not taking mechanical design or any sort of fatigue analysis class, then this information is still extremely helpful. Okay, so like I said, in statics, we learn how to analyze the entire system, okay, namely, of course, the forces and moments within those systems. And we are now concerned with the following three things. We are concerned with stress, deflection, and failure. Hence, the name of the course is called Mechanics of Deformable Bodies or Mechanics of Materials. Okay, so in order to kind of help you guys wrap your heads around what I call the flow of D-Forms, I'm going to list all 6 steps and their importance, okay? So the first thing that we need to analyze in any system, remember, if you haven't taken the statics crash course with me, then I highly recommend that you do so, okay? So I introduce my methods of solving mechanics problems to you, and these types of methods can be used throughout your entire engineering curriculum, not just statics, okay? So, in the beginning, when you see any engineering system, anything, it could be, like I'm looking at random things, a bike rack, a keyboard stand, a fruit basket, okay? If you look at anything, any mechanical system, it doesn't even have to move, right? You need to look at it and say, okay, what is going on here and how does it work, okay? And the first thing that you need to understand while you're doing that is the external forces acting on the system. Okay, the external forces acting on the system, okay, which include the applied forces and moments, right? So it must be like the gravity, right? So the weight of the object that's pulling it down, or perhaps there's like a twisting moment on there, so external forces and moments, right? And of course, the reaction forces, like the normal force that the wall would push back against a picture frame, or the ground, which pushes up against the fruit basket, okay? So that is strictly statics, right? So in statics, we talked about equilibrium, and the equilibrium is a result of the reaction forces balancing external applied forces and moments, okay? The next thing we're going to look at is what is going on internally. Internally, which we, of course, we name as internal forces. Of course, internal forces and moments, right? So just not to include internal forces and moments, which, if you recall, when we looked at machines, we asked, oh, what is the force inside the pin? Or we looked at trusses, say, what is the force inside, section BG, okay? We also understood this in statics, okay? Another place where we looked at internal forces and moments was in our shear body diagrams, right? When we talked about beams. So when we talked about beams, we said that shear is when a beam breaks like this, and moment is when a beam breaks like this, or experiences this type of force and this type of moment. Okay, so we analyze the inside of beams using this type of idea right here. Okay, then the next thing that we're going to do is understand stress. Okay, now note that external forces require knowledge of the stuff that's being applied to it, right? So external moments, external forces. In order to understand internal forces and moments, we had to consider the geometry of the beam itself. So for example, we're gonna stick with the beam, right? We needed to know how long the beam was, where the forces were being applied inside the beam, and so on and so forth, okay? When we introduce stress, okay? When we are concerned about stress, stress is strictly based on the internal geometry, okay? So internal geometry. What does that mean? When we talked about the beams and pretty much everything in statics, we did not say, hey, the cross-sectional area of this section is, a square or a circle, okay? We did not care about what the cross-section looked like. All we cared about was the forces that were going on inside. Once we're looking to analyze stress, we suddenly care about the internal geometry, okay? And that is going to be one of the first things that we talk about in deforms, okay? That's going to be a deforms topic. So we care about the internal geometry, okay? And I'll say the stress has units of newtons per meter squared, right? As you can imagine, newtons comes from the external forces and the internal forces and moments, and the meters squared comes from the internal geometry. In other words, the cross-sectional area of our piece, okay? After that, we care about deflection. Okay, so not only do we care about the internal geometry, what's going to tell us how much it's going to deflect by is the material property. Okay, the material property, which is going to be, for example, the stiffness, right? That's going to require us to know the stiffness. Okay, of course, the deflection is going to be in meters, right, or millimeters, whatever you want to call it. Okay, and this is again going to depend on material properties. Okay, so for example, if I have this thing right here and I'm squeezing it, right? It's a foam roller, right? So if I squeeze it like this, the inside is going to experience some amount of stress, right? And the stress is, of course, we're going to have a whole lecture on this, is going to be the force divided by the cross-sectional area, which is whatever force I can apply to it, divided by the cross-sectional area of this. Now, if this were made out of marshmallow, it would just go like, right? It would shrink, right? Because the marshmallow is very soft, okay? But that has nothing to do with the amount of stress, because that has to do with the material properties. Now, if this were made out of steel, if I try to squeeze it, it endures the same amount of stress that the marshmallow one did, but it doesn't shrink as much because the material property is much more stiff, okay? The material is much more stiff. So, after deflection, we look for failure, okay? And this is what we call immediate failure. Okay, immediate failure has to do with our loading conditions, okay? So we are interested in, oh, by the way, deflection is still deforms, okay? We'll be covering that in this class. Immediate failure basically says, hey, what is the maximum force or stress that this particular thing can hold? If it exceeds that, boom, it's gonna fail immediately, okay? It will just fail, boom, right off the bat, okay? So that has to do with loading conditions. Okay, also deforms. Okay? After immediate failure, if something doesn't fail immediately, you know that it could eventually fail over time, right? And this will be long-term failure. Okay? So of course, like your car, you drive a car, okay? You drive it off the lot, brand new car. You say, oh, it's not gonna break because right, it didn't fail immediately, but after you drive it for a few years or something, something might break. Why? Because something happened between the time that you bought it and the time that it broke that ended up weakening or changing the properties or stress and loading conditions, okay? And the long-term failure is based on such as environmental factors, right? So for example, if you endure a lot of temperature cycles, right? Cold, hot, right? Like the leather seats in your car, right? You know, in the summertime it's hot, in the wintertime it's cold, cold, hot, right? And then your leather gets all brittle and stuff like that, right? Is it exposed to a lot of moisture, right? Like your steel could potentially corrode if you expose it to a lot of moisture, or if you expose it to chemicals, right? Like just any, like salt water, for example, right? Is very corrosive to steel. Even stainless steel is not perfectly resistant to salt water, okay? After that, there's a cyclical behavior too, because if I take this marker and I bend it back and forth, right now it's not gonna break, but at some point it's gonna break, like a paper clip, right? You can bend a paper clip back and forth a few times. What happens after you bend it back and forth 20 times? It's gonna break, okay? Eventually it will break, okay? And lastly, we have, of course, temperature effects, like I mentioned, is just if something is super hot, it doesn't necessarily have to be a cyclical temperature effect. It could just be, is something super hot, as you guys probably already know from chemistry, that steel gets a lot softer when it's super hot, right? So if you have a pipe that has a pressure rating, then if the fluid flowing through it is extremely hot, then the pressure rating actually goes down, right? So you need to actually use a stronger pipe for the fluid as the fluid gets hotter running through it, okay? So in D-forms, we are going to focus on stress, deflection, and failure, okay? Those are the three things. The two things that we already covered are external forces and internal forces from statics. So we will be covering stress, deflection, and failure, immediate failure, inside here, okay? And the last thing, this long-term failure will be covered in mechanical design. All right, so your mechanical design course will say, take into account all of these factors. And a lot of the stuff is empirical, right? So it'll be experimental. You'll just come up with some really nasty equation that says, oh, if the temperature goes up by 1 degree Celsius, what is my maximum stress change by? And these are all the kind of things that you will learn in mechanical design. Okay, great. So moving on, like I promised, the first thing that we are going to cover in this class is stress, okay? And stress is not just something that you get from going to engineering school. It is something that materials experience when you apply forces and moments to them, okay? There are 4 types of stress in this class, all right? So I will say, right? Our stress is, like I mentioned before, newtons per meter squared, okay? Otherwise known as a Pascal, okay? Okay. Now, there are 4 types of stress that you will learn in this class, okay? Now, it's already written in the notes, so I will go through them with you using the hand signals. So for those of you who have taken the statics crash course, we know that I said shear was like this, and moment was like this, okay? So we are going to expand that idea towards stress. So the 4 types of stress are, number 1, normal stress. Ready? This is normal stress, right? So the material is pressed up against each other. This is the cross-sectional area, so it just goes like this. Boom, okay? And the equation for that is sigma equals P over A. Okay? That is normal stress. Remember, boom, normal stress. Okay? The next type of stress is what we call bending stress. As you could already imagine, it looks something like this. Okay, so notice how it's not like this anymore, but my hands are still pressed up against each other, right? If I go like this with my bending stress, the top of my knuckles have more stress than the bottom, and if I go like this, the bottom, right, my thumbs, will have more stress than the top, okay? So that is bending stress. The equation that we use is my over I, with m being the moment, y being the some distance, which we'll talk about when we get there, and then I being the area moment of inertia, which we learned how to calculate in statics, okay? This is a sigma sign, right? So this is, sigma is normal stress, okay? So bending stress is a normal stress, right? It's just a normal stress that changes throughout the cross-sectional area, okay? So that's how we use sigma for both of these, because like I said, if I go like this, then the top experiences a greater pressure per se than the bottom, okay? And we'll go into more detail about this later on. This is just to help you visualize the similarities between normal and bending stress, okay? The other types of stress, one is going to be called direct shear, or it's simply just shear, right? And this is going to be equal to tau equals VQ over IT. Okay, and again, we'll talk about all these in a second. V is the shear that we found from statics, right? The shear moment diagrams, we use the capital letter V. That is the shear. Q, we'll talk about, first moment of area. And then this is the area moment of inertia, as we expect. And then T is a geometric measurement that we'll talk about again. So direct shear, how can we show direct shear with our hands? Well, it is like this, as you expect, right? So if you want to shear something, it'll just be boom, right? That is shear, okay? So that is direct shear. Oops. And the last one that we are going to cover is torsional shear. Which is TR over J, okay? With T being the applied torque, R being the radius, and J being the polar moment of inertia, okay? So it's not the moment of inertia in the X or Y direction, it is the moment of inertia in the Z direction, okay? And this can be represented by doing this. This is twisting, right? So twisting stress, okay? So these are the 4 types of stress, and these are the only 4 types of stress that you are going to see in this class, okay? So every single time you see a system, you should be able to describe every single part of the system either by doing this, 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 or this, okay? So these 4 things will be able to describe every single situation that you have in engineering mechanics. Will there be a combination of these at times? Sure, right? We'll talk about combined loadings. I believe it is lecture 6. Okay, so we'll talk about combined loadings in that lecture. But for now, we are going to tackle these individually. But before that, we have a couple more things to talk about. All right, so one thing I want to talk about is the average stress versus stress profile, okay? So I just want to make a quick note, average stress versus stress profile. That's not how you spell profile. Average stress versus stress profile. Now, a lot of times you'll find that you calculate the average stress, okay? So the average stress just says throughout the whole cross section, this is the stress. It just turns out to be like this, okay? But in reality, well, let's use this and you'll see why in a second. So in reality, the stress profile actually looks something like this, where the maximum stress is tau max, okay? And this is, by the way, this is in relation to shear. We'll go into this in more detail when we talk about shear. I believe that is in lecture 6 also, okay? So the maximum shear occurs somewhere inside the cross section, but sometimes we'll consider the average shear. But let's look carefully. Just because the average shear is low doesn't mean that the maximum shear is going to be low as well. So we have to be a little bit careful when looking at numbers. We have to make sure that we make it clear if it's the average stress or the maximum stress from the stress profile. Okay, that's just a quick note. We'll go into more detail about that later on. All right, so the next thing I want to talk about before we move on to stress and strain is the factor of safety. So the factor of safety is typically written as FOS. It could also be written as FOS, okay? Most commonly, it is written as the letter N. So if you see the letter N in D-forms, most likely it will mean factor of safety, okay? So as I have it written in the notes, I have the failure stress is equal to the factor of safety times the allowable stress. Okay, if you put it into a form that you solve for N, you get the failure stress divided by the allowable stress. Okay, and of course you can do the same thing with your tau. So you can write tau failure divided by tau allowable. So what does that mean? Okay, so our allowable stress is what we're actually going to put on the system. All right, and your failure stress is going to be the actual failure point of the system, and that failure point is going to depend on your internal geometry. It's going to depend on your primarily material properties, right? So if we think the most common thing that comes to mind is A36 steel, which is like a standard grade low carbon steel, which is what like structural steel, like you'll see in buildings and things like that. The failure stress of that steel is 36,000 pounds per square inch, or 36 KSI. This is going to be your failure right here. So if I want to calculate my allowable, right, then my allowable stress is only going to be 18 KSI. Right? So it says, hey, if my steel is going to fail at 36 KSI, then the maximum allowable stress that I'm going to put on my system is going to be 18 KSI. Okay? And long story short, why do we use factors of safety? Well, in a nutshell, it's because shit happens. Okay? Really. Because when we manufacture this steel, it's not guaranteed that the steel is going to have a 36 KSI maximum yield strength throughout its entire length. Okay, what if there's a little chip in some parts, or what if a little bit of it rusts and it goes down to 34 KSI, right? So I wouldn't be comfortable putting anything more than, for example, 18 KSI on this structure, okay? So here are some typical values of N, or typical factors of safety for various systems. For airplanes, we use N equals 1.5 to 2.5, although I've heard that N's can typically go down to 1.25. So you're probably wondering now, holy moly, right? My plane only has a factor of safety of 1.5 or 1.25. Like, it seems kind of counterintuitive, right? That planes, which if you're in a plane crash, the survival rate is almost 0, that they would use such a low factor of safety. But in reality, there's two primary reasons that planes use such a low factor of safety. First is because of weight, right? You want to make the plane as light as possible, okay? Because obviously otherwise it wouldn't fly, right? And the other reason, most importantly, is because they make sure that the materials that they use for the plane are the highest quality materials, right? So for example, if you purchase a bolt for a plane, right? Let's say a typical bolt like this for a plane, okay? There is a certification number, okay? Somebody has inspected it, they've done all the paperwork, there is an entire report for this one single bolt that comes with it, okay? So that's how they know it's certified, and you know for sure that the failure stress is exactly the failure stress. So you know it's gonna be exactly, let's say, 100 KSI before it fails, okay? But whereas if you go to Lowe's and you buy some random bolt off the shelf, it'll say 100 KSI, but if you drop it on the floor, it might become 80 KSI, or if you jiggle around the box a little bit, it'll become 50 KSI because there's some defects during the manufacturing process that affect its longevity. Okay, so that's the reason why planes have such a low factor of safety. Okay, for other things such as buildings and bridges, we don't really care too much about the weight, do we? Right? So therefore, it's much cheaper. Well, because think about it. If you had to buy a bolt with a certification on it, then you would expect this bolt to be a lot more expensive than just buying a bolt from Lowe's. Okay, so that's the reason why sometimes it's actually cheaper to use a higher factor of safety, because you don't need all the paperwork that comes along with certified materials. Okay, so if you buy uncertified materials, like if you go to Lowe's and you buy lumber, right, if you're rich, okay, you can go to Lowe's and buy some 2x4s. There's no certification that says, hey, this wood definitely doesn't have any knots in it. It will definitely hold this much weight. Like, nobody's gonna certify that. That's why lumber is fairly cheap, okay, compared to things that are actually certified, right? So that's one thing. And like I said, why factor of safety? Shit happens, right? So I went over this already, but it's because materials are not perfect, okay, unless they manufacture them to be very, very tight tolerances. You just don't know how a material is gonna hold up in standard manufacturing process, okay? So the question is, how do we find the allowable force and weight? Okay, so find out what will cause failure. Okay, so find out what will cause failure, which is essentially like, okay, if we have this plane, right? We know that if we load the plane with 400 people, right, in a simplified case, we load the plane with 400 people, it's going to fail, okay? So, of course, this is extremely simplified. If we want a factor of safety of 2, then we would only put 200 people on the plane, okay? So it's sort of like when you drive over a bridge, it says like maximum weight, 36 tons, okay? So if you drive 36 tons over the bridge, odds are you're gonna be fine, okay? Because they usually build bridges with a huge factor of safety, okay? So like I said, 4 to 7, and sometimes you could even build it to like 10, okay? So you won't break it, right? But they place that limit there for a reason, okay? So in case, you're a truck and you just don't give a crap, you can just drive over the bridge and nothing will happen, right? For safety reasons. Okay, so now that we've got the factor of safety out of the way, we will be utilizing this idea throughout the course, of course, finding the maximum stress in various types of design. We will incorporate the idea of factor of safety. So this is just an introduction, all right? And the next thing I want to talk about is strain. So strain is the percent increase in size or decrease, so in the size of an object, okay? So how do we calculate the percent increase or decrease? Well, it would just be the change divided by the original length, okay? And the change we call as deflection, delta. Okay, so deflection, and then our length is just the original length, right? Of course, the deflection and the original length have the exact same units, so therefore our strain epsilon is unitless, or sometimes we call it millimeters over millimeters. Other times you'll see it as millimeters over meters, okay, which says like, oh, a 1 meter long stick got compressed by 1 millimeter, okay? So you'll see sometimes the units like this. If you see an epsilon without any units after it, you can assume that it's either millimeters over millimeters or meters over meters. They're the same thing because they turn out to be 1. This, if it is millimeters over meters, it will tell you after it gives you the unit, okay? So, strain can be caused by several things, okay? So of course, changing the length of something can be caused by a few different things. Causes temperature, right? So for forces, I'll follow the order of the notes, right? So forces, like I mentioned before, if I take my foam roller, right, and I squeeze it, okay, I can reduce, I'm not strong enough, but you can squeeze it and reduce the length by a couple millimeters, or I could pull it and lengthen it by a couple millimeters, okay? Alternatively, temperature can be used I'm sure many of you are familiar with thermal expansion or thermal contraction, right? When materials get hot, they tend to expand. When materials get cold, they tend to contract. So that is going to be a form of strain. Okay, we will have a section that talks about the thermal strain and thermal stress. Another one is pressure. Okay, so pressure meaning, right, it could be sigma, okay, which of course is related to force and cross-sectional area, but it can also be like the pressure in a balloon, right? Obviously, if I blow into a balloon, the more pressure, the bigger the balloon gets, so that is going to be a strain in the volume, right, volumetric direction, okay? And of course, there are many other things that can cause strain, but these are the ones that we are going to focus on in the class. And of course, strain is a function of the material properties, okay? So strain, as you can see, is deflection, right? We talked about deflection in the flow of deforms, and we said that deflection is dependent on the material properties, okay? So the material properties, there's two primary material properties that we are going to be discussing in this class. The first is E, Young's modulus. E, Young's modulus, also known as the stiffness of the material. Okay, it actually has the same units. It has units of newtons per meter squared. Okay, and the other one that we are going to talk about is G, shear's modulus. Right, shear modulus, which also has units of newtons per meter squared, okay? So the shear, as you can imagine, right, Young's modulus has something to do with this, and the shear modulus has something to do with this and this, okay? So that's the reason why we separated our types of stress into sigma stresses and tau stresses, okay? So that's the reason why, because there's two separate properties that determine what is going on here. And of course, a normal is like this, it's pressing versus sliding, okay? So pressing here, sliding here, okay? So this is Young's modulus, this is our shear modulus. Excellent. So I gave you guys a bunch of these equations now, so there's a whole bunch of stuff going on here. Let's talk about how they're all related, because yes, you are given a formula sheet in this class. You can take formula sheets to the exams. I'm almost positive that's still the way it is. At least it was when I took the class. But if you guys understand where the equations come from and how they kind of all intertwine, then a lot of these equations become common sense, all right? So I'll do my best to try to explain to you all that, right, like why this equation is the way it is, and then we will relate it to the other equations. Okay. So we have the shear equation as epsilon equals delta over L. Then the other equation is going to be this, sigma equals epsilon times E, and E being Young's modulus, and epsilon being this, the strain, which makes sense, right? The units for sigma are going to be stress, which is newtons per meter squared, okay? Epsilon is unitless, and then E is newtons per meter squared, right? So this equation makes a good deal of sense here, okay? And now we know that if sigma is equal to P over A, because remember, like I said in the previous slide, for normal stress, sigma equals P over A. If we combine these two right here, we end up with this, okay? So you may be wondering, well, that doesn't really help me a whole lot. Well, let's replace this epsilon with delta over L. Okay, delta over L. So if we solve for the delta, what we get is delta equals PL over AE. What does this equation tell us? This tells us for a certain cross-sectional area of a certain material that has some length, how much force, how much axial force can I put on it, right? So like this, before it deflects, okay? So back to my foam roller example. right? My foam roller has some stiffness, okay? If I look up the Young's modulus of this foam, I can get a value and put it here. If I have the cross-sectional area, which I can just take my ruler and just calculate the cross-sectional area using pi r squared. I know the length, I can measure the length of this. I think it's an 18-inch foam roller. And then the amount of force. So how much force can I push on it, right? So compress or expand, right? So I can pull on it. And if I know all those values, I can calculate how much it's going to stretch by, all right? So that is one of the equations that we are interested in, okay? And that kind of brings us to our strain, okay? So, or brings us to our example, excuse me, right? So let's use these equations and solve the example on page 3. Okay, this is a fairly simple example. We have all right, so in this problem, we are going to find the strain and then the deflection, okay? So we're given everything, okay? So we know that this is a rod, a cantilevered rod that is stuck to the wall, and we know that the cross-section is just a circle with a diameter of 1 centimeter, okay? So with that, we can note that we can find the strain. Now, if we look at the strain, okay, the equation for strain that we used is going to be sigma over E. All right, so remember before we said the equation was going to be sigma equals epsilon times E, but now of course if we're looking for strain, we just calculate, solve for epsilon. Okay, now do we know sigma? Okay, we don't know the value of sigma, but I do know that sigma is equal to P over A. Okay, and I believe I do note that the material, oh here, I said underneath, I said the material is steel, right? So the Young's modulus of steel is equal to 200 gigapascals. So 200 gigapascals, which if you're not familiar with giga, it is 200 times 10 to the 9 newtons per meter squared. Okay, so in deforms, you should become very familiar with kilo, mega, giga, right? So those are kind of the 3 ones. Kilo is 10 to the 3rd, mega is 10 to the 6th, and giga is 10 to the 9th. Okay, so those are the big boy units that we will often use in this class. Okay, so this is the stiffness of steel. So all we have to do now is just plug in all of the numbers. Okay, so we have epsilon equals the force, which I know to be 1,000. Note that this is a force that's causing this thing to stretch, so it's going to be a positive force, so 1,000, divided by the area. What is the cross-sectional area of my piece? Well, I can use pi r squared, or, right, so you guys already know the area of a circle is pi r squared. In the notes, I have it written as pi over 4 times d squared, okay? Now, of course, I didn't do this just to frustrate you guys. I did this because this is just another way to solve for the cross-sectional area. If you're given the diameter, all you have to do is divide by 4, right? So pi over 4, right? It's just another way to show you guys, just to give you some variety, because I know you all know how to solve the area of a circle. Okay, divided by E, which is this, 200 times 10 to the 9th newtons per meter squared. If I solve this out, I get my deflection to be 6, it's going to run out of space, but 6.366 times 10 to the negative 5 meters per meter, okay, or millimeters per millimeter, right? So a pretty small deflection, okay, a pretty small, or not deflection, sorry, a pretty small strain, all right? So if I look at this and say, okay, well, this is the strain. Remember, this is just the percent elongation, all right? So it's 6.366 times 10 to the negative 5 meters for every meter. Okay, that's going to be the strain. But if I'm interested in the overall deflection, it's simply going to be my epsilon multiplied by L. Because as you remember before, epsilon is equal to delta over L. I just multiplied my L to the other side. Okay, so because I know what this value is, I can go ahead and multiply it by my length, which is 2 meters, and I find to be 1.27 times 10 to the negative 4 meters. Okay, so what is this like in your head? This turns out to be 0.013 centimeters, which is, as you can imagine, very small. Another good thing, a unit to know in this class is a micrometer, which is, say 1 micrometer equals 10 to the negative 6 meters. A micrometer is also known as a micron, all right? So if you hear someone say, oh, it's 100 microns, it means 100 times 10 to the negative 6 meters, all right? So if we were to rewrite this in microns, it would just be 130 microns. Okay, so that, of course, if you're talking to someone who does a lot of microphysics or micromechanics, microfluids, they would know exactly how big 130 microns is, but to us normal folks, that's not something that we're able to imagine, okay? Sort of like 200 times 10 to the 9, right? Okay, so that is the idea of strain, okay, and deflection. Of course, using the most basic example possible. We will revisit this idea after the second lecture. So in the third lecture, we will revisit this idea. This is just a simple, straightforward example to show you all the relationship between epsilon, sigma, p, a, delta, and all this other stuff. Okay, so it's one of those sections where if you know the equations, you can just plug and chug. But I want you all to understand how the equations are related, because that's how you understand deforms. And the whole point of this class and the way I teach it the way I do is because I want you to understand how changing different aspects of your design will change the outcome. Okay, so if you're trying to build something that does this, this, and this, and meets this and this parameters, you can use your knowledge of deforms and the logic that I'm trying to teach you to say, oh, all we need to do is change the area or change this shape to be this. Okay, so I want you to have the intuition. All right. Okay, great. So the last thing I want to talk to you about is shear strain. Okay, so we talked about normal strain, where something stretches and compresses. What about shear strain? Okay. All right, so shear strain is the idea that if you have a material, right, so normal strain would be like pressing it like this or like this and kind of compressing it like this or compressing it like this. Shear strain is what happens when you apply a force this way and it kind of shears across like this, okay? So let me show you an example. All right, so I have this box here, right? It's just a paper wrapping thingy, right? So when I apply a top force to it, right, I know that it's going to squish, right? So that's normal strain. And there's also a way to do it that goes like this too, right? But what if I apply a shear force to it? Remember that shear force is like this, right? So what if I just apply a shear force and it goes like that, okay? So it's a normal rectangle, and then when I apply a shear force to it, it becomes a parallelogram, all right? And that's exactly what we're going to consider here. Of course, we're not going to consider the forces or the material properties yet. We're just going to talk about shear strain itself, all right? Which is going to be described with the following. Of course, this is a huge exaggeration. As you can see, this is only 3, and this is only 2. Okay, and this angle right here is going to be gamma xy. By the way, this is a gamma, all right? We frequently refer to that as the angle, right? Angle of change, sort of like we refer to delta as the change in length. We refer to gamma as the change in angle. Okay, so we need to say, okay, well, what is gamma xy, right? What is gamma xy, and what is this new angle, right? Theta prime. Because the initial angle is just 90, right? So which is why this 90 is right here, okay? Now, we can say that gamma xy is equal to, okay, so how do we figure that out? Well, this is the same angle as this, okay? Would you guys agree? So these are both gamma xy, all right? So I know a little bit about this triangle right here. I know that the opposite side is going to be 3, so arctan of 3 divided by this distance right here, which I know the total distance is 250, and I know that it got shortened by 2. So it's going to be 250 minus 2 as my arctan, which I find out to be 0.0121 radians. So 0.0121 radians. Okay? And then what we can see is we can actually also find the normal strain, our epsilon. Our epsilon normal strain is simply going to be AB, okay, minus AB prime, which I should actually note that AB prime, B prime is right here, okay, is going to be .00793 millimeters per millimeter. Oops, millimeter. Right? So note that a radian is dimensionless, by the way. I'm not sure if any of your math professors have covered this. A radian is dimensionless, as is millimeters per millimeter. Okay. And how do we find what AB and AB prime are? Well, AB is just this distance of 250 millimeters. AB prime is equal to what? Is going to be equal to the square root, because this is a right triangle, right? So essentially we're looking for this distance right here, which is the same as this distance, right? So it's going to be the square root of essentially 250 minus 2 squared plus 3 squared. Okay, so if you take these numbers, you plug them into here, you'll find strain to be that. All right, and that is it for shear strain. So during the next lecture, we'll go over a bunch of different strains. Okay, we'll go over all that different stuff. But to recap, in this lecture, the most important part is talk about the flow of deforms, and we talked about the 6 different steps that we need to take in order to analyze systems, right? First looking at the external forces, then looking at the internal forces. After that, we look at the internal geometry to understand the stress, and then we look at the strain based on the material properties, and then we looked at the immediate failure, which has to do with the immediate loading conditions. And then, of course, in the next course, mechanical design, right, we will look into mechanical failure, long-term mechanical failure, which occurs from different environmental factors such as temperature, cycling, and all that other good stuff. All right. And then we talked about the 4 types of stress that we will cover in this class: normal stress, which looks like this; bending stress, which looks like this; shear stress, right? So direct shear, which looks like this; and then torsional shear, which looks like this. Okay, so those are the only 4 types of stress that we are going to be covering in this class. And we could use those 4 types of stress to describe every single mechanical system out there. Okay, and the last thing that we talked about was a strain and deflection example with a normal rod, right? So we're talking about lengthening and or shortening, right? So we calculated the deflection and strain for that. And the other thing that we did was our shear strain example here. Note that we really don't use this shear strain equation that much in the class. We mostly focus on our normal strain, okay? And next class, we're going to be going over strain in a little bit more detail. We'll be talking about more of mechanical properties of materials, the stress strain curve, ductile versus brittle materials, and we'll also be talking about Hooke's law and Poisson's ratio, okay? And with that, I'll see you all next time.